All right, so welcome to this talk about advanced integration patterns and their trade-offs. Thank you for joining today. I'm really glad you found the time to be here. And before we start with the actual content, let me also quickly introduce myself. So I'm Dirk, and I work in Amazon Web Services as a principal solutions architect. And in my role, I work with customers and help them on their cloud journey, provide guidance on software architecture and technology strategy. And while I'm also trying to look at my customers through the glasses of their CTO, CIO, or even CEO. But next to my work with customers, sorry, my hobby horse is actually serverless technology and particularly software architecture approaches for building highly scalable systems that are resilient and flexible. So I created this content together with my colleague Gregor Hoppe, who is a senior principal evangelist for serverless at Amazon Web Services and quite well known also as an international expert in integration and software architecture and software strategy. So during the talk, you will find a few quotations, insights, or just comments from both Gregor and me, and also from some other relevant persons. And I will often enrich our own sayings with a situational role or mood we were in when we made them. And you will see what I mean during the talk. A few things about housekeeping. First thing is I will mention a few concrete integration products here and there for illustration, mostly messaging systems. And you don't necessarily have to know these products in detail. I'll try to provide the necessary context. And it's mostly about point-to-point messaging with queue and publish-subscribe messaging with topics and buses. Second thing is I will most likely need the entire 45 minutes of our slot here for my content. So if you have any questions or you want to discuss something with me, please feel free to just type them, your questions into the chat here, or even better, reach out to me via LinkedIn or Twitter, and I will respond to you during the week. All right, now let's dive into the content and have a look at some nice vacation pictures I took last year. Because, and that is true for many areas of life, one of our major beliefs is that we can learn a lot about systems architecture from the real world. And when you look at this picture here, as a tourist, you probably see a big red rock in the middle of the desert. However, as a software architect, you will probably spot a monolith. It's impressive, but it also comes with a slew of issues. And when you ask me what I'd count as the most prominent issues, I will say excessive coupling between components and a lack of cohesion within each component. But why is that so? Well, monolithic applications that have grown over time almost always show a lack of encapsulation of their components. Also, the decomposition into components might have been right in the beginning, but often it isn't anymore after several rounds of evolution. And this can manifest as spaghetti code and leads to an increase in coupling between components. And that also means a decrease in cohesion within each component. All this has a negative impact on several quality criteria. And a prominent symptom is that deployments take ages. They are error prone and need manual intervention. Such a degradation can be one of multiple drivers for companies to decide to change the architectural style towards the divide and conquer approach. The usual suspects, of course, here are microservices or self-contained systems. But I don't really want to stress the term microservice too much here, and I personally prefer to talk about systems or services in general. Okay, so the main point here is in that such a transition, components from the monolith turn into independent services. And that's also, by the way, a good opportunity to work on the encapsulation and maybe fix the existing decomposition. Now, coming back to how Mother Nature can inspire us. Check this out. Nature has actually started to decompose this monolith. It carved out the first service, and that's what many companies do too for a start. Carve out one service that brings a lot of pain in the existing architecture. And over time, one can break the monolith into many more services. And eventually, the architecture will look more like this: a landscape of independent services, like the one we see here with these beautiful hoodoos on the photo. And these services or systems may belong to one overarching application, which may have been a monolith previously. But it can just be any system in your IT landscape that you operate, or a landscape of systems. Now, in both cases, these systems will have to be integrated and interact with each other. Some of them might have closer interactions, while others are farther away from each other. And the more distance, the more coupling is typically needed. The systems with the blue circles that are quite far away can be external third-party systems, maybe SaaS solutions. And the point here is that also outside of the context of a microservice-based application, the question of integration is something that every company has to deal with virtually everywhere and across any layer. So even by looking at nature, we can learn one important lesson here. In modern cloud applications, integration isn't an afterthought. It's rather an integral part of the application architecture and the software delivery lifecycle. So again, outside of the overall scope of big distributed applications, there's integration challenges to manage. The way you integrate your system also has an implication on your software delivery. And the more your systems are decoupled, the more it is possible to evolve and deliver your systems autonomously and frequently, which is also quite important. And it's probably quite known that many of the big tech companies deployed several thousand times a day. But you may ask yourself, okay, but I'm not Amazon, and that's totally right. Still, you don't have to deploy like every other second, but you would probably want to deploy quite often. There are several reasons for this, like reducing the risk with small changes, catch errors quickly, and also faster time to market, for instance, which gives you a competitive advantage. So the reason why I'm saying all this is to stress that the way you integrate your systems has a decisive influence on if such a short delivery life cycle is even possible for you. Okay, so as anywhere in software engineering and architecture, things are a lot easier to grasp and discuss when you're talking in patterns and concepts, like using a lingua franca. And this is more valuable typically than talking about concrete tooling. And when you deal with software development, you're certainly familiar with pattern catalogs like the Gang of Four catalogs. And when it comes to integration, there are also several standard integration patterns that you can use to reason and implement your integration upon. And we will encounter some of those in the remainder of the talk. So why don't we actually start with some patterns? Let's have a first look at some of them that discuss rather fundamentally different approaches to integration and different interaction models. It's actually super easy to draw a line between two systems, but integration actually takes many shapes. You can see a few examples here. We make a lot of fun of file transfer. However, much of the world still runs on it. It's reliable and it works with almost any technology. Shared databases are really brittle, but you will find them everywhere. And APIs are all the rage until a tree of RPCs brings your systems down. Gregor, my co-author here, has written a whole book about messaging, and now many folks use streaming, for instance, for IoT. So there's also quite some ambiguity on which to select. And of course, we also need to coordinate all this via choreography or orchestration. Oh my, and that's not even all. Because that simple architecture picture here can raise a lot of complicated questions once you start digging into that one connector between those two systems. I just mentioned APIs or interaction models like RPC. Is that interaction synchronous? Does it show the data flow or the control flow? As we will see later, these two sometimes even point into the opposite direction. So all in all, there are tons of options for integration that require a stable navigation and consideration. One will not find any option that fits well for all use cases. In fact, with integration, it's not any different than with any other architecture or technology decision, or with anything in life in general, for that matter. And this brings us to the next insight. No architecture decision you take comes without trade-offs. Every architecture decision brings you pain, unfortunately. And your job as a software architect is to identify the least painful option on the table. I know we all want something that just solves all our problems without any adverse effect. But unfortunately, we all need to face this unpleasant truth. There is no silver bullet in software architecture, and you should always beware of the faith healer. That means a tool or a person that promises you just use this and all your pain will be gone. And that applies also to what I said in the beginning. You might find that I didn't give the monolith architectural style enough love. Maybe, well, yes, there are some cases where a monolith is the right decision, and there's no always and there's no never. But when you bring all the trade-offs to the table, you will see that for your particular situation, it's either a good decision or it isn't. And experience has it, though, that more often than not, a monolith is not the best decision, but applying the principle of divide and conquer will help you more. And then if you do that, you will have to work with a distributed system. So why don't we look at a distributed system now from an integration patterns perspective? Let's focus on 4 fundamentals here, which is coupling, control flow and flow control, message order and delivery semantics, error handling, and replace. And let's just start with coupling, which is indeed the integration's magic word. So we have, again, our nice and simple architecture of 2 integrated systems. And when they are tightly coupled, it means that making a change in one system will force you to make a change in the other system too. If you want independence and flexibility, on the other hand, you want to integrate these systems with loose coupling. Obviously, the most successful way to decouple 2 systems is to not integrate them at all, which is obviously not an option if you want them to interact with each other. But when we want to integrate the 2 systems in a loosely coupled manner, we will have to pay for this independence and flexibility with something else, both at design time and runtime. And coupling is really multi-dimensional. So diving into the details of this overview could again fill an entire talk. So let's only mention a few things here. A classic root of pain is the data format and data type dependency. Probably all of you have experienced it before. And one that can have a big impact on overall resilience is the temporal dependency that you can influence with whether you have a synchronous or an asynchronous integration. We will look at this more with an example in a minute. And for many of these cases here, at least for the ones that belong to design time, however, if coupling is harmful or not depends on one thing. The appropriate level of design time coupling depends on the level of control you have over the endpoints. And as an architect, we must understand the trade-offs. In this case, the trade-off is level of control. And if I control the change on both sides, because I am building all the parts of a distributed system myself, I can afford a higher level of coupling than when I'm integrating with a third party. Now, moving on to some runtime coupling. If you haven't heard about message queues yet, here is one. So what it does, a queue, is to decouple two communication parties in a way that both don't have to know anything about each other anymore. It's a point-to-point channel in the sense that every message is delivered to one consumer. And there can be concurrent consumers, even on the right-hand side, that compete for messages, but still each message reaches one consumer. In that sense, you can even see a queue as a kind of load balancer in front of those competing consumers. A queue enters the scene as a logical communications channel and decouples the location of a message receiver from the message sender. So that is one of the reasons why A on the left-hand side doesn't have to know anything about B on the right-hand side. And furthermore, it also decouples the message sender from the availability of the message receiver, as it can buffer messages in case the receiver is offline. And in that sense, the queue can even be seen as a buffering load balancer in front of competing consumers. Overall, the passing of messages also decouples interaction style and data format dependencies. The message body as such frees you from considerations like big endian or so. And it also reduces the interaction to simple primitives like send messages and receive messages that are operations for everyone. I will talk about queues in a few times in the remainder of this talk, and sometimes I need to be a bit more concrete and use Amazon SQS or Apache ActiveMQ for illustration. And for those who don't know those services, Amazon SQS is a cloud-native and serverless message queue service in AWS that is designed for almost infinite scale. And Apache ActiveMQ is a more server-based messaging system that you can use for traditional applications as well. All right, so to illustrate this a bit more, and to also understand it better compared to a classic API-based scenario, let's have a look at a practical example now. And the example is a fictional ride-sharing service. You probably all know what a ride-sharing service is. And in our example, the fictional company runs marketing campaigns about making their customers pre-book their future rides already in advance. And they have started this use case with the following rough architecture that is based on APIs and synchronous communication. So we have the rideshare service customer on the left-hand side. The customer uses an application and they send the details for their future booking, for their pre-booking to a backend that is cloud-based, and the request reaches the ride booking service. So the current call to action from the marketing campaign is book your ride for next week, already this week. And the ride booking service decomposes all the activities that come with the processing and makes use of a number of downstream services to help them fulfill everything. So first is there's a request going out to the resource management service that makes sure, do we actually have the resources to fulfill the ride? Then there's a request going to the ride payment service. That one, again, contacts the fraud detection service to check if something might have been wrong with the customer in the past. Probably we use an external payment service provider. And last but not least, we also want to make sure that the customer gets points with the customer loyalty service. Each of those activities here take a bit of time. And that are actually a lot of activities, and they pile up. And we use synchronous APIs here. That means the entire request processing time that we pile up here is dependent on how long each activity in the downstream services actually takes. And due to the nature of synchronous API requests here, we will bind resources in every service along the request path. In worst case, as long as the overall request processing takes. This may work fine with low or medium load or so. And as long as the marketing campaign says, book your ride for next week, just anytime this week, we should be good. But now the marketing team changes the call to action, and it is now book your ride for next week already today, or book it already now within the next 10 minutes or so. And then we would experience a load concentration. And now our architecture reveals the downsides of synchronous integration. It blocks resources, as I said already, in all involved services. And as I said, worst case for the entire time the request processing takes. It means it tightly couples the involved systems for the time request processing takes. And in addition to that, problems that might occur downstream can accumulate upstream. And this is why there are mitigation patterns like circuit breaker in the first place. So particularly under load, a synchronous integration approach can jeopardize the reliability of the entire application. And it can require excessive horizontal scaling with a respective cost attached. So what did our sample ride-sharing company do now? Well, they worked on reducing their runtime coupling or temporary coupling by switching from sync to asynchronous communication. And now each downstream service immediately acknowledges a request and then only starts working on it. Obviously, still, the processing in each service, each step takes some time. But now the one that calls a downstream service doesn't have to actively wait for it anymore, and no resources are being blocked. Now you might ask yourself where the eventual response is here. Of course, it will have to come. It will have to come eventually, but it would overload this diagram here. I will show the response in one of the subsequent diagrams where it is better to digest. But the point here is, with all this, we have reduced the runtime coupling between the systems quite a bit and have gained more independence for scaling and operating each of our systems here. And with this change in our integration approach, we also have a foundation that our overall system can remain stable, even if the load becomes high. Which brings us to the following insight. Friends don't let friends rely on synchronous integration. So that's good. Unfortunately, and I'm sorry to say this, even after turning an API-based integration from synchronous to asynchronous communication, there's still coupling involved that can lead to problems. And let's look at it again, and now focus only on the first level of downstream services to simplify the diagram, which brings us here. So first level of downstream services, resource management, right payment, and customer loyalty. So we still have the asynchronous HTTP requests going to each downstream service. And the most obvious coupling aspect we still have stems from the availability dependence that exists for integration via APIs. Apparently, two parties cannot communicate via APIs if one of them is offline. But how can you then handle planned or unplanned unavailability in our integration architecture? Well, as you remember, a queue is a point-to-point channel. So let's see what happens if you replace these APIs with messages over dedicated queues now. Now, by doing this, the write booking service is no longer talking directly to the downstream services. And the queue characteristics eliminates the availability dependence. And as I said before, I still owe you the responses to all those requests that go back upstream. And I'll show you them now. And as you can see here, that there's a response queue for each of those downstream services too. Now we can scale and also update services independently. In case one service fails, becomes overwhelmed or unavailable, or we just want to limit the resource spent, we can process the messages at another point in time, consume slower, or just consume faster. But how do the downstream services actually know where to send their responses? And how does the write booking service actually know which response message belongs to which previous request? So for that, we have the patterns of correlation ID and return address. Both patterns relate to meta information that is injected into the messages, and due to their names, they should be quite self-explanatory. And you would have used them already with your asynchronous API approach before. Now, with our downstream services decoupled, we can come to the following insight. Loose coupling is mostly better than lousy coupling. And I would personally tend to say always instead of mostly, but as I said in the beginning, beware of the faith healer, in this case, me. And there is basically no option that is always the best one. And it always depends, like the typical architect answer, but that's the truth. Of course, there are cases where tight coupling is more advantageous or even required, or it's simpler and it is affordable. But for sure not when your workload needs to function at scale or you need flexibility. Okay, with that, let's move on to the next aspect, which is control flow and flow control. So we can typically distinguish between the data flow between two systems and the control flow that manages the interaction between the data or for the data flow. So apparently the data flow in our case is that data is sent from A to B, and the messaging control flow basically follows this. But if you think about remote procedure call, for instance, you have the control flow of a request and response. If you go to polling, for instance, the control flow is initiated by the consumer side. And this brings us to the insight that control flow is really essential to understanding dynamic system behavior, and that targets on aspects like latency and scaling, batching, and timeouts. Let's have a look at queues in that respect again. One of the nice things is that they can act as traffic shapers. I said in one of the previous slides that queues can act as a buffering load balancer. So in that respect, they can actually flatten peak loads, which is super helpful. And if you look at the arrival rate curve here on the top left side, it looks quite different than the consumption rate. So the queue can make it quite comfortable for the consumers to allow the consumers to consume messages at their own individual speed. Well, that's the sunny case, right? Then there can also be a rainy case. If you have very fast producers, the arrival rate goes through the roof. And if your consumption rate stays at the same level, your queue fills up, which may or may not be a problem. That is basically dependent on your context, on your application, and particular on the messaging system that you use, right? So first of all, if you use a cloud-based messaging system like Amazon SQS, you don't really have to worry about queue size or so, because it is virtually indefinite. If you use an instance-based messaging system like ActiveMQ, you will have to deal with that because then your storage is finite. What tools and patterns do we have to help here? So apparently there's always something like a time to live. You can apply this to messages. You can make your messaging system automatically remove expired messages. And even for very important messages, there is eventually a point in time when they don't make sense anymore. So you can use this as a means to mitigate. But then also there is a way to inform a fast producer to become slower. And this is called back pressure. Like a nice example for this is actually the queue in a Starbucks shop. So if you order your coffee, then the associate that takes your order fills the queue with placing mugs or cups that contain your name in a queue on the espresso machine. And once that queue is full, so all baristas are super busy with it, they should probably not accept a new order until the queue has emptied a little bit. And if that is your pain point, you have to deal with back pressure and work on that. So for Amazon SQS, time to live is something that comes implicit, but back pressure has to be built. For a system like Apache ActiveMQ, you can also use some automation here, like producer flow control that instructs the fast producer to slow down, but then you only shift the problem to the producer code. You still have to deal with that information somehow and make sure that you don't process your messages so fast. So the essence of this is that, yes, queues are a super helpful thing for decoupling. But then one of the trade-offs that you need to face here, you need to think about flow control. And this is another example of a coffee shop. This time not Starbucks, but at our AWS customer conference, AWS reInvent last year, where we had also a virtual coffee shop with serverless technology that also illustrates the idea of back pressure quite nicely with a state machine that takes care of the operations of the orchestration of the particular steps. And then there's one step in the middle, capacity available. If that is the case, yes, then we can continue. If not, then there is back pressure, and customers will be throttled a few seconds from ordering more coffee. Okay, so the insight here, queues decouple control flow, but they require flow control. Right, let's move on to the next aspect, order and delivery semantics. And we start with FIFO channels. And let me also introduce this topic with a provocative statement. Message order is frequently demanded, and from time to time, even with good reason. And this is simply to express that we tend to demand everything, every functionality without thinking too much about it because we are lazy and we just want to have it all. But maybe we don't need it, and many times we don't need a certain feature. How can FIFO queues even work or operate, and what does it cost us? So what does it mean? FIFO, first in, first out, if you're not aware of that. And we want to get a strict order for message delivery for that. So the messages in the order, they came into the FIFO queue. We also want them to be delivered to consumers outside. Order exclamation mark, which is something that always reminds me of John Bercow. I don't know if you remember that person. It was the former Speaker of the British Parliament who celebrated to use that word. And as always, all magic comes with a price theory. So what's the price you pay for your strict order? The more you scale out your messaging, the more it becomes difficult to impossible to guarantee strict order for message delivery. And this has nothing to do with technology or code quality. It's rather the law of physics. And if you want to guarantee strict order, you need to reduce concurrency and/or scope at a certain point in time. And this is why FIFO queues cannot have the same throughput as standard queues. And also there's another pattern that helps reduce the scope, which we will inspect in a bit. But first, let us have a look at what actually happens if we have multiple consumers on a FIFO queue. And if we use a naive approach for FIFO queues without any other helping pattern around it. So we have in this example 3 concurrent consumers, and we have the FIFO queues and 4 messages. So let's just play through what happens. First message is delivered to a consumer. It's in processing. The second and the third message likewise. Now, all 3 messages ABC are being processed, and look at that. Message A was faster with processing than, message B was faster with processing than message A. And this is why it ends up on the first position in our log. Okay, second consumer is free again, so it can receive message D and continue with that. Then message A is done, message D is done, and eventually message C is also done. So as we can see here, the message processing time can vary and lead to order violation in our consumer processes. So without any other helper around it, if we just employ a dumb FIFO queue, we have no guarantee that our message order is really retained after processing. Maybe there's a pattern we can employ here that can help here. Yes, there is, which is the message group pattern, and which is a discriminator attribute that we can add to our messages. And the example I'm going to play through here is Amazon SQS message group IDs. So that's a piece of meta information that comes with every message, and it determines the assignment of a message to a certain message group. And you can define your message groups like arbitrary. And in our example, we have 3 message groups, which are represented by different colors in the messages, the blue, the green, and the orange one. So the behavior is as follows. We receive message A, we receive message B, both are being processed. Message B is again faster with processing, and it appears in our log on the first position. Now, what happens next? We don't receive message C, although it would have been the next one in the order. Now, the way how message groups operate is that as long as one message from a group is in processing, or we also call it, it's an in-flight message, we don't deliver a message of the same group to a consumer. And this is to preserve the order at least within every message group. And this is why message D appears next. It's being processed. Now message A is done. And now we can also continue with message C. So everything is being processed and appears in our processing log accordingly. Now, you might say, well, we still didn't retain the original order. Yes, that's true. And this is how message groups operate. What we have reached, though, is that we retained order within each message group. And that allows you to scale out your consumers on the right-hand side on the number of message group IDs, which also leads us to the insight that the order of messages in a distributed system is really relative to a defined scope. In our example, the message group IDs. There's the term local versus global message order. What we have just shown here is local message order based on message groups. What if a global message order is needed? That means the order across all messages, across all time, across everything. Well, you can use one message group for all messages, but still it is the global part is still relative because there apparently cannot be an order across everything, right? So in practical messaging systems, you need to limit this order to a certain time window, for instance. But if you say, no way, I absolutely need a totally global message order, then you will pay for this by falling back to sequential database writes. That's the price you pay for it. Okay, next item, deduplication and how often delivery. Again, the provocative statement, message deduplication is frequently demanded from time to time, even with good reason. So there are situations where you must have this, no doubt about it. But our mental laziness, again, makes us want it all the time, which ignores the trade-offs. What if you process the message halfway? Do you want it to be redelivered? Is a big question you should ask yourself. Again, practical patterns and helpers to implement this for Amazon SQS FIFO queues would be a message deduplication ID on the consumer side. And this is limited to a 5-minute interval. And on the consumer side, it is the receive request attempt ID that will also help consumers to receive the same message multiple times. But then there's also something like a timer, which is called the message visibility timeout. So in other words, this means also deduplication of messages in distributed systems is relative to a defined scope. And you have to be aware of this, of this trade-off in this case. Let's go through one example for this. So are you looking for an exactly once dingus here? Even if we use all deduplication options for producers and consumers, in this case, we have 2 nice messages and a FIFO queue. So what can still happen? Let's see. So we have 3 concurrent consumers. One of them gets the first message. And now during processing of the message, 3 steps are run through. First thing is write something to a database. Okay, works. Second one is doing something else with the downstream system. And unfortunately, we run into an exception. Now, the question you need to answer for yourself is now, what behavior do you want now? Do you want to be super strict and exactly once delivery? Then you would say, okay, forget about that message. I don't want to have my messaging system to redeliver that message for another attempt. Or do you want to face reality? And obviously, you need to have this message redelivered to process it afterwards, maybe after you have fixed your code on the second system here. And there's one insight again that you can derive from that. If you require exactly once delivery, you end up back at synchronous integration or shared database. And there's one pattern that you might already feel below all this, which is an idempotent consumer, which I recommend to have anyway. But let's look at this one also from the perspective of error handling and replay, which is the final aspect here. And there's one sub-aspect here, which is poison pills and dead letter channels. Something that also every architect should be aware of. Everything fails all the time, and you need to prepare for this. And one pattern in messaging that can help you here is a dead letter queue. What does it do? So if you experience an exception during processing of a message repeatedly with the same message, we call that a poison pill. And that doesn't necessarily have to be something wicked or so. It can be just a transient failure mitigation, or it can be a problem in your consumer code. So you don't want to have an endless, infinite loop here with redelivering the message and running into an exception. And therefore, you can use the concept of a dead letter queue. And that frees you from an open heart surgery. The message is rerouted to that particular dead letter queue, and you can investigate about the root cause for the failure without the hassle of production. And yet another main insight here, since you cannot prevent failure anyway, you should prepare yourself for it. So embrace failure and use all the tools that you have. By the way, there's one common pattern that is employed virtually always when something goes wrong somewhere, which is retry. And while it is totally valid and encouraged, you still need to do it with care. One insight we gained about it is the following. No mechanism brought more distributed systems down than retry logic. All right, and I have one last aspect for you, archive and replay. So let's have a look at where it can help you and what you need to pay for it in return, the trade-off. What we have discussed so far in terms of error handling is how to deal with a poison pill while we do message processing. Now, what if we detect only after all message processing and consumption is done that our consumer processes did something wrong? So let's have a look at the example. So we have our messaging infrastructure here. We use bus this time. Typically, the concept of archive and replay is implemented with fan out or pub sub systems. In terms of AWS services, that would be Amazon SNS, FIFO topics, or Amazon Event Bridge message bus. Let's use a message bus here for the example. Producers create those messages A to D. They go to the message bus, and the message bus not only delivers them to the consumers, but also stores them in an archive. And if you want to add more resilience for your consumers, you can also add a queue in front of them. Now, you discover a bug in your consumer code, and the messages have already been processed, but in a wrong way already, unfortunately. And that means they are not available anywhere in the bus or in the queue. So the queue protects your consumer from being overwhelmed and keeps messages for a while, but once they are acknowledged or consumed, they are gone. Okay, now you fix the code, and then you can use the archive to replay those messages. And if your consumer wants to figure out if it has seen one of the replayed messages before, you might want to rely on something more abstracted than a message ID that you might have used in the past. So you should always abstract from a technical ID to a non-technical ID, like a business ID, and so on. But the thing here is that you, in any case, receive messages a second time. And therefore, again, the price you pay for it, the trade-off that you need to invest here is you have to have idempotent consumers. And you also need to think about downstream systems. Will they be able to handle with the reprocessing? So the main price you need to pay for this is that you really need to implement the idempotent consumer pattern. And this doesn't necessarily have to be super complicated, but it's something that we not always have on our minds. All right. So if we do a reprise of the principle from the beginning, still, no architecture decision you take comes without trade-offs. Every architecture decision comes with some pain. And your job as a software architect is to identify the least painful option on the table. And with that, I'm done with what I brought for today. In case you're interested in getting your hands dirty a bit more on the context of loosely coupled systems, you can take a look at our hands-on workshop, Decoupled Microservices. It picks up the idea of fictional ride sharing that we briefly looked at in the first half of this talk. And it makes it really magical by using unicorns as vehicles that replace the traditional taxi cabs. And if you are an AWS customer that is supported by an account team, you can also ask your friendly AWS solutions architect to run an application integration immersion day with you if you feel that it unblocks your progress on that front. And other than that, I want to thank you again for joining today. I hope you find the content a bit useful. As I said in the beginning, please feel free to reach out to me if you have questions, if you want to discuss something. And not only at AWS, we are data-driven, also the JCon conference is data-driven. And as such, your opinion matters greatly to our improvement efforts. So please use the opportunity to provide your feedback through the conference website. And also let me know where I can improve for next time. Thank you again. Have a great day and a great rest of the conference. Bye-bye.